Hello and welcome to this series of lectures on numerical optimization. In the next few lectures, we will study about convex sets and convex functions. Remember that these convex sets and convex functions play a very important role in the optimization theory, and it is very important to understand this theory before we actually move on to the other problems. So, let us start looking at convex sets first and then the convex functions. Convex functions are very nice functions which do not have problems of local minima, as we will see later. Now, these convex functions are typically defined on convex sets. So, we first study convex sets before moving on to convex functions. Okay. Now, before we get on to the actual theory of convex sets, so let me define some notations. So, on the display you will see a line drawn passing through the points x 1 and x 2, where x 1 is not equal to x 2. Now, associated with each of the points on the line is a parameter lambda. So, let us assume that lambda is 1 at the point x 1, lambda is 0 at the point x 2, and beyond x 2 the value of lambda decreases. So, here you will see that for this point lambda is equal to minus 0.2 and it decreases further as we move away from x 2 in this direction. Now, if we move away from x 1 in this direction, the value of lambda increases. So, any point on the line will have some real lambda associated with that point. So, the line passing through x 1 and x 2 can be represented by a set y, such that y can be written as lambda x 1 plus 1 minus lambda x 2, where lambda belongs to the set of real numbers. So, if we plug in lambda equal to 1, what we get is y is equal to x 1 as this quantity vanishes. If we plug in lambda equal to 0, we will get this quantity vanishes and we get y equal to x 2. So, a line is parameterized by a parameter called lambda, which is a real number, and one can if we are given 2 points through which the line passes, one can appropriately set lambdas at those points and find the equation of a line which passes through these points. Now, if we restrict ourselves only to the line segment x 1 and x 2, then we will denote it as ls x 1 comma x 2, and that can be written as y is equal to lambda x 1 plus 1 minus lambda x 2. Now, remember that lambda takes the value in the closed interval 0 to 1. So, unlike the line where lambda can take any value from the set of real numbers, here when we talk about the line segment, lambda takes the value in the range 0 to 1. So, this is the line segment x 1 x 2 that we are talking about. Now, let us look at what are called affine sets. A set x which is subset of R n is said to be affine if you take any 2 points in the set x 1 and x 2 and take any lambda which is a real number, then lambda x 1 plus 1 minus lambda x 2 should belong to x. So, what this essentially means is that if you take any 2 points from the set x and take a line passing through those 2 points, then that line lies in the set x. Okay. So, such a set is called an affine set. Now, this definition can be generalized to the set of k points. So, earlier we took only 2 points x 1 and x 2. Suppose we take k points x 1, x 2 up to x k, which are part of the set x, and if we choose lambda which are lambda i's. So, there will be a lambda associated with each of these points, but if we choose those lambdas such that sigma lambda equal to 1, then if x is an affine set, then sigma lambda I going from 1 to k belongs to the set x. So, this is just an extension of this. So, remember that when we have an affine set, we take any points, any set of points from that set, then sigma lambda xi is 1 if we ensure that sigma lambda is 1 for the affine set. Now, here are some examples of affine sets. So, if we consider the solution set of linear equations, so where A is a m by n matrix and B is a m dimensional vector, then the set of all x such that x equal to B forms the solution set of these linear equations. Now, one can easily show that this set is an affine set. For example, if we take two solutions x 1 and x 2 of this system of linear equations, then a x 1 equal to B and a x 2 equal to B. So, if we take lambda, so lambda into x 1 plus 1 minus lambda into x 2, one can show that that also satisfies. So, if we take any x such that x equal to lambda x 1 plus 1 minus lambda x 2, that also satisfies the system A x equal to B. So, any solution set of linear equations of this type is an affine set. Another example of an affine set is a subspace or a translated subspace. For example, so this is a vector subspace, because you will see that it is in two dimensional space. This is a vector subspace because it passes through the origin. Now, if I translate it, that becomes an affine space. Now, both are affine sets, because if you take any points, any 2 points in this set, then the line passing through those points belongs to the same set. So, these two both are affine sets. In fact, one can show that if we have an affine space and if we translate it to the origin, then it becomes a vector subspace. So, here is a result which says that if we have an affine set x and let us take a point x 0 from that set x, then the set of all points x minus x 0 where x belongs to the set x, it forms a subspace, and it is very easy to prove that. So, let us look at the proof of this result. So, let us consider the set y. So, we are given x naught which belongs to the set x. So, let us consider the set y such that which is the collection of x minus x naught where x belongs to x. Now, we have to show that y is a subspace. That means that what we have to show is that by the definition of subspace, if you take any two vectors say y 1 and y 2 in the set y, then a linear combination of those two vectors should also belong to the subspace y. So, that means that if we choose alpha and beta belong to R, then alpha y 1 plus beta y 2 should belong to y. So, this is what we want to show that y is a subspace. Now, so let us consider y 1 and y 2 which belong to the set y, and let us consider two scalars which are real numbers alpha and beta. Now, since y 1 belongs to y and x naught belongs to x, so y 1 plus x naught clearly belongs to x, and similarly y 2 plus x naught belongs to x. Now, let us see what happens to alpha y 1 plus beta y 2. So, alpha y 1 plus beta y 2 can be written as alpha into y 1 plus x naught plus beta into y 2 plus x naught minus alpha plus beta into x naught. Now, you will see that y 1 plus x naught belongs to x, y 2 plus x naught also belongs to x, and x naught obviously belongs to x, that is given to us. So, all these three vectors belong to the set x. Now, is this a affine combination of these vectors? Let us sum the coefficients which are here. So, alpha plus beta minus alpha minus beta. So, that is 0. So, that this is not a affine combination of the vectors in x. So, what we do is that to make it an affine combination, let us add x1, x0. So, once you add x0, so what do we get? So, these quantities remain the same, and the one x0 gets added to the third quantity. Now, you will see that y 1 plus x naught, y 2 plus x naught and x naught belong to x, and this is a affine combination of the three vectors in the set x, because alpha plus beta plus 1 minus alpha minus beta is 1. So, clearly alpha y 1 plus beta y 2 plus x naught belongs to the set x. because this is X is an affine set and we are considering an affine combination of 3 vectors in that set. So, clearly this left hand side quantity belongs to the set X. So, which means that alpha y1 plus beta y2 should belong to the set Y. So, since X is an affine set, the left side quantity belongs to X and therefore, alpha y1 plus beta y2 belongs to Y, which implies that Y is a subspace. So, if we have any affine set and if we translate it to the origin, then it becomes, so clearly you will see that since x0 belongs to X, origin also belongs to the set X minus x0. So, clearly origin is a part of the set Y, and by this proof it is a subspace. Now, let us look at some more definitions. Suppose we are given a set of points x1 to xk. Now, a point x is said to be an affine combination of points in X if you can write X as a linear combination of the xi's, and the linear combination is such that sigma lambda is 1. So, the sum of the coefficients in the linear combination should be 1. Then we call X to be an affine combination of the points xi is I going from 1 to k. Now, then one can talk about this affine hull. So, affine hull is the set of all affine combinations of the points in X, and it can be written as a set of all affine combinations of xi's in X. So, remember that sigma lambda is going to be 1. So, you take any k points in the set X, take an affine combination of them and collect all possible such affine combinations, we will get a affine hull of the set X. Now, we will move on to the definition of convex sets, and as I said that this convex sets and the convex functions are very important topics in the theory of optimization, and some of these ideas are used to derive optimality conditions for general linear and nonlinear programming problems. Okay, so, let us see the definition of a convex set. Now, a set say which is a subset of Rn is said to be convex if you take any 2 points x1 and x2 belonging to that set and a scalar lambda such that 0 less than or equal to lambda less than or equal to 1. So, lambda lies in the closed interval 0 to 1. Then we have lambda x1 plus 1 minus lambda x2 which belongs to C. Now, what does this definition mean? So, this definition means that if we take any 2 points x1 and x2 from the set C and take a line segment joining x1 and x2. So, lambda x1 plus 1 minus lambda x2 where lambda is in the closed interval 0 to 1 denotes a line segment joining x1 and x2. So, if you take any 2 points x1 and x2 belong to C, take a line segment joining those 2 points, that line segment should entirely lie within the set C. So, let us look at some examples. So, here are a couple of examples of convex sets. Now, you can think of convex set as the following, that along the boundary, suppose if we put a wall along the boundary of a given set, if we put a wall and then consider any 2 points in that set, then any 2 points. So, every point should see any other point of the set directly through a straight line path. So, if you take any 2 points here, then and if we take a line segment joining those 2 points, that lies entirely within that set. Similarly, one can say that this is a convex set. Now, let us see some examples of non-convex sets. So, on the left side you will see that if I take this point and this point, so the line segment joining these 2 points does not entirely lie within the set, although some part of it lies, but not the entire line segment should lie within the set. So, if we again go by the earlier geometric interpretation, suppose if we put a wall around the boundary, then this point will not be able to see this point because of the wall. Similarly, this is not a convex set because the line segment joining these 2 points is not entirely within the set. So, these are some examples of non-convex sets. So, here is one more example. So, let us consider the set of points in 2-dimensional space x1, x2, where x2 is nothing but x1 square. So, this is the set of points which is shown by the green curve here. So, this set is not convex because if I take a point here and take a point here, the line segment joining them is not part of the set. So, these are some examples of non-convex sets. So, for convexity what we need is, for convexity of a set what we need is that the line segment joining any 2 points of that set should lie entirely within that set. Now, let us look at some more examples of convex sets. Now, by convention the empty set is a convex set. Then any singleton set is also a convex set, because since we have only one point in the set is obviously a convex set, because there is no notion of line segment in that set. Then the set of the set Rn, the n-dimensional set of real numbers, these are all convex sets. Now, if we take a closed ball in Rn, the ball with center x naught and radius r, where r is greater than 0, or if we take a open ball in Rn, where which has a center x naught and the radius r, which is again greater than 0, they are all convex subsets of Rn. Now, any affine set is a convex set, because an affine set by definition is a set where if you take any point, 2 points, the line passing through the 2 points always lies in that set. So, if a line passes through the set, the line segment joining any 2 points also should lie in that set. So, affine set is also a convex set. Then the line segment, if we just consider line segment is a convex set, but the line segment is not affine, because the entire line does not lie in that set. So, a line segment is a convex, but not affine. Now, it is possible to construct some new convex sets using given convex sets. So, then we will have some ways to derive new sets, new convex sets from the existing convex sets. Now, before we look into those details, let us look at some definitions. So, let P and Q be subsets of Rn and let alpha be a real number. Now, the scalar multiple alpha p of the set is defined as the set of all points x such that x is nothing but x equal to alpha p, where p belongs to p. So, we take given alpha, which is a real number, we take every p from the set P and multiplied by alpha and get x. Now, collect all such x's from all possible p's, that will form the set alpha p. Now, similarly, one can also define the sum of 2 sets as p plus q is nothing but you take a vector p or a point p from the set P and vector q from the set Q and then sum them up. So, this is a vector sum of P and Q. So, collects all such x's from all possible pairs of P and Q, where P belongs to the set P and Q belongs to the set Q, and that will form the sum of 2 sets P plus Q. Now, with these definitions, we can generate new convex sets from the given sets of convex sets. Okay. So, let us look at some results to generate new convex sets. Now, if we have a collection of convex sets denoted by Ci, where I belongs to the set A, then the theorem says that then the intersection of these convex sets is a convex set. So, let us try to prove this result. So, let us consider the set C to be the intersection of all Ci's where I is from the set A. I is the index set, I is the index which belongs to the set A. Now, let us consider the first case where C is empty or singleton. Now, we have seen that by convention, if C is empty, it is a convex set, or even if C is singleton, it is a convex set. So, we have to worry about only those cases where C is non-empty and non-singleton. So, let us look at that case. Now, whenever we want to show that any set is a convex set, what we need to show is that for any 2 points in that set and lambda in the closed interval 0 to 1, lambda x1 plus 1 minus lambda x2 should belong to C. So, this is what we need to show. So, let us consider any 2 points in the set C. Now, since they are in the intersection set C, they are in the individual sets as well for every I belong to A. Now, remember that each of the Ci's is a convex set. So, by using the convexity of Ci, what we can do is that we can say that lambda x1 plus 1 minus lambda x2 belongs to Ci for every I belong to A, and where lambda is in the closed interval 0 to 1. This is because of the fact that every Ci is a convex set. Now, that means that if we take a line segment joining x1 and x2, that entirely lies within the set Ci for every I. So, which means that if we take the line segment joining x1 and x2, it should also lie in the intersection of these Ci's, because it belongs to every Ci. So, which means that lambda x1 plus 1 minus lambda x2 belongs to the intersection of all Ci's for all lambda in the range 0 to 1, and this intersection of Ci I belong to A is nothing but the set C. So, lambda x1 plus 1 minus lambda x2 belongs to the set C for all lambda in the range 0 to 1. So, this result says that if we take a collection of convex sets, any collection of convex sets, then their intersection is a convex set. So, by using given convex sets, we can try to take their intersection and form new convex sets. So, this is the first result that we saw. Then the second result is about the sum of two sets. So, suppose if we are given C1 and C2 as convex sets, then C1 plus C2 is a convex set. So, as I said earlier, that to show that any set is a convex set, we need to take 2 points in that set, any 2 points, and show that the line segment joining any 2 points lies entirely within the set. So, let us consider x1 y1 belong to C1 and x2 y2 belong to C2. So, these are the vectors in C1 and C2 respectively. So, we can say that x1 plus x2 belongs to C1 plus C2 and y1 plus y2 belongs to C1 plus C2. This is by the definition of C1 plus C2. So, now we have got 2 points in the set C1 plus C2, and what we need to show is that lambda into x1 plus x2 plus 1 minus lambda into y1 plus y2 also belongs to C1 plus C2 for all lambda in the range 0 to 1. So, this is what we need to show. Now, so remember that what is given to us is that C1 and C2 are convex. So, if I take 2 vectors x1 and y1 in C1, then the line segment joining x1 and y1 lies in the set C1. So, if I write Z1 to be lambda x1 plus 1 minus lambda y1, so Z1 clearly belongs to C1 for all lambda in the range 0 to 1. And similarly, if I take 2 vectors x2 and y2 in the set C2 and take a line segment joining x2 and y2, I can write Z2 to be lambda x2 plus 1 minus lambda y2, which belongs to C2 for all lambda in the range 0 to 1. So, now we have a vector z1 which belongs to C1 and a vector z2 which belongs to C2. So, what we can do is that we can sum them up. So, z1 plus z2 will belong to C1 plus C2. So, this is the important point, that z1 plus z2 belongs to C1 plus C2. And what is z1 plus z2? Now, if we sum the right side, what do we get? So, remember that x1 plus x2 belongs to C1 plus C2 and y1 plus y2 belongs to C1 plus C2. So, if we sum this the right side, what we get? Lambda into x1 plus x2 plus 1 minus lambda into y1 plus y2, and that is nothing but z1 plus z2. And since z1 plus z2 belong to C1 plus C2 from 1, what we get is that the vector on the right side also belongs to C1 plus C2 for all lambda in the range 0 to 1. So, we had 2 points x1 plus x2 in the set C1 plus C2 and y1 plus y2 in the set C1 plus C2, and a line segment joining those 2 points, which is written as lambda into x1 plus x2 plus 1 minus lambda into y1 plus y2, also belongs to the set C1 plus C2 for all lambda in the range 0 to 1. So, which means that C1 plus C2 is a convex set. So, if we are given 2 convex sets, we can generate a new convex set. For example, if we take x axis in a 2-dimensional space, if we take x axis as one convex set and the y axis as one convex set, then the set C1 plus C2 is entire R2, and that turns out to be a convex set. So, new convex sets could be generated by taking the vector sum of the convex sets easily. Now, here is a third result which says that if C is a convex set and alpha is a real number, then alpha C is a convex set. Again, it is very easy to prove that. So, let us take 2 points in the set C and show that the line segment joining these 2 points also belongs to the set C. So, let us take x1 and x2 in C, and since C is convex, which is given to us, lambda x1 plus 1 minus lambda x2 also belongs to the set C. Now, if we take alpha x1 and alpha x2, where alpha is a real number, now clearly this alpha x1 and alpha x2 belongs to alpha C. And what we have to show is that the line segment joining alpha x1 and alpha x2 should also belong to the set alpha C. So, if we take the line segment joining alpha x1 and alpha x2, which is represented as lambda into alpha x1 plus 1 minus lambda into alpha x2, we can rewrite it as alpha into lambda x1 plus 1 minus lambda x2, and this is nothing but a point in the set C. So, this alpha into this quantity clearly lies in the set alpha C for any lambda in the range 0 to 1. So, which means that alpha C is a convex set. So, this theorem tells that new convex sets can be generated by shrinking or expanding the given convex set appropriately. Now, let us look at the definition of hyperplane. So, suppose B is a real number and A is a non-zero vector in Rn, then the set of all H such then the set H is the set of all x such that A transpose x equal to B is said to be a hyperplane in Rn. So, let us see the significance of each of these terms in the set H. Now, the vector A denotes the normal to the hyperplane, and if now the norm of A is 1, then the modulus of B, the absolute value of B, is the distance of H from the origin. Now, in R2, in 2-dimensional space, hyperplane is a line, and in 3-dimensional space, a hyperplane is a plane, and in higher dimensional cases, we call this as a hyperplane. So, if we draw a line in 2-dimensional space, it is a hyperplane. So, again let us consider a 2-dimensional case, but the ideas are essentially the same for high dimensional cases. So, we have vector A which is pointing in this direction, and let us consider the set which is shown by the black line as the set of all points x such that A transpose x equal to B. So, this is A transpose x equal to B is an equation of this hyperplane, and if we collect all such x's that forms the set H, that is called the hyperplane. So, remember that A is normal to this hyperplane. Now, if you are given a point which belongs to the hyperplane, then this equation of the hyperplane can be written as so if x0 is a point which lies on the hyperplane, and we are still talking about the normal to the hyperplane as A, then the set of all x such that A transpose x minus x naught equal to 0 forms the hyperplane. So, you will see that if we take any vector on this and form the vector x minus x naught and take a dot product of that vector with A, the dot product since they are perpendicular, any vector here and any this vector A, they are perpendicular to each other or orthogonal to each other. So, their dot product is 0, and that is what is reflected in the definition of this hyperplane. So, it is just another way to represent a hyperplane if you know a point x0 which belongs to the set to the hyperplane, and if you know the normal A to the hyperplane. Now, if you are given a set S, if you are given some function f which is differentiable, and the contour of that function, so the contour of that function we are denoting it by S such that set of all x such that f x equal to f of x naught, because the contour passes through the point x naught. So, all the points on this contour will have the value of the function to be equal to f of x naught, and as we move in the interior the value of the function decreases. So, this is denoted by the set S minus. So, it is basically the set which is in the interior of this, where f of x is strictly less than f of x naught. So, as you move in the interior, the value of the function decreases. As you move away on the other side, away from this curve, then the value of the function increases. Now, if we take a point x naught which belongs to this contour, then we can approximate this contour by a hyperplane. And if we use the first derivative of the function, remember that we have assumed that the function f is differentiable. So, if we use the first derivative of the function, and this vector g is a gradient vector of f at x naught. So, gradient of f of x naught is nothing but g of x naught. So, then one can use the first order approximation of s at x naught as the set of all points such that, so now we have a normal to the hyperplane and the hyperplane passing through the point x naught. So, set of all x such that g of x naught transpose x minus x naught to be equal to 0. So, this is going to be the first order approximation of the function of a differentiable function f at point x naught. So, we will require this sometime later when we derive the optimality conditions. So, just wanted to show that the first order approximation can be represented in the form like this. Now, let us look at half spaces. So, the set H plus, which is a collection of all x such that A transpose x is greater than equal to B, where A is again a non-zero vector in the space of n dimensions, and B is a scalar. The set H plus is called a closed positive half space generated by the plane H, hyperplane H. So, remember that the equation of the hyperplane H is set of all x such that A transpose x equal to B. So, we are just considering the set of all points which lie on one side of this, which lie on or on one side of this hyperplane. Similarly, one can define the negative half space, set of all x such that A transpose x less than or equal to B. Now, we will show this geometrically. So, we have a hyperplane H, and this A is normal to this hyperplane. A is so the hyperplane is a set X such that A transpose X equal to B, and the points, so the set of points which lie on this side of this hyperplane where A is pointing, that is called the positive half space. So, the points on the hyperplane and on this side of the hyperplane is called a closed half space. Now, if we make the inequality strict, that is the set of all x such that A transpose x greater than B. So, these are the points which are not on the hyperplane, but are on the this side of the hyperplane. So, that is called a open half space, open positive half space. Similarly, one can talk about the closed negative half space. So, again we are given a hyperplane whose normal is A, and so the points on this hyperplane and points on the other side of the normal, they form a closed negative half space. So, now with these definitions of half spaces, let us look at some more examples of convex sets. So, the hyperplane is a convex set. So, it is obvious because if you take any 2 points on the hyperplane and the line segment joining those 2 points always lies in the hyperplane. Now, let us consider m vectors in n dimensional space and m scalars b1 to b2. So, a1 to am are the m vectors, and suppose we arrange them in the form of a matrix where every row is a the ith row denotes the transpose of the vector ai. So, you have m by n matrix and B is a m dimensional vector. Now, the claim is that the set of all x such that x equal to B. So, if we want to solve this system of equations x equal to B, then the solutions of that system of equations, it forms a convex set. Now, it is obvious because Ax equal to B, this set can be written as A1 transpose x equal to B1, A2 transpose x equal to B2 and up to AM transpose x equal to BM. Now, we have already seen that set of all x such that A transpose x equal to B is a convex set. So, each of AI transpose x equal to BI, I going from 1 to M is a convex set, and what we are doing is that we are trying to take an intersection of this convex sets, and the as we have seen earlier that the intersection of convex sets is a convex set. So, the solution set of the system of linear equations x equal to B, where A is a matrix like this and B is a vector like this, it forms a convex set. Now, if you take closed half spaces, either positive or negative, both are convex sets. Now, again using the ideas similar to this, we can show that the set of all x such that Ax less than or equal to B, or the set of all x such that X greater than or equal to B, they form convex sets. Now, here is a simple example. So, let us consider a hyperplane, although I haven't shown arrows, but this is a hyperplane, and then suppose we are interested in the closed half space of this formed by this hyperplane, the closed half space pointed by this arrow. Okay. So, clearly this is a convex set. Now, let us consider another hyperplane. So, this is another hyperplane and we are interested in the closed half space of this hyperplane, the half space which is formed which is denoted by this arrow. Now, if we take the intersection of the previous the half space and the current half space, so it is basically the area between these two, it is the region between these two hyperplanes, and that also is a convex set. And if you add one more, so we get a triangle in this 2-dimensional space. So, the interior of this triangle is a convex set. So, So, by using the existing convex sets, it is possible to construct new convex sets, and that is illustrated here. Now, let us look at the definition of a convex hull. The convex hull of a set S, of a general set S, is the intersection of all convex sets which contain S and is denoted by convex hull of S. So, it will be denoted like this. Now, by the very definition of convex hull, you will see that it is the intersection of all convex sets, and we know that intersection of all convex sets is a convex set. So, every convex hull is a convex set. In fact, if we are given a set S, then sometimes we would like to form a convex set which contains S, and such a convex set, which is the smallest convex set, is called the convex hull of the set S. So, many times these convex hulls are used for convexification of a set S without bringing in any redundancy. So, a convex hull also can be thought of as the smallest convex set that contains the given set S, and we will see some examples. So, if you are given 2 points, then the line segment joining those 2 points, it is a convex hull of the set of those 2 points. Now, if in 2 dimensions, suppose if you are given x axis and a y axis, then the convex hull of these 2 sets is a entire 2 dimensional space. Now, when we studied convex sets, we saw this example, and we demonstrated that this S is not a convex set, but now one can form a convex set of this set. So, that becomes this set. Now, this set is a convex set. As you will see that you take any 2 points in this set, it will always form a that line segment always lies in the set. Now, here is another example which we saw that this is not S is not a convex set, but then one can find a convex hull of this set. And suppose we are given a set of points, and if you want to find the convex hull of this. So, it is the smallest convex set that encompasses all the points. So, this is the smallest convex set which encompasses all the points. So, remember that the points in the interior, they are not used in forming the convex set or representing the boundary of the convex hull. So, here is one more example, that we consider the set x1 x2 such that x2 equal to x1 square. So, this was the given set, and the convex hull of this set is the set of points on this curve and the points above this curve. So, the shaded region here plus the points on the curve, that together forms the convex hull of the set. So, this is basically the set x1 x2 such that x2 greater than or equal to x1 square. So, we will stop here, and in the next lecture we will continue with the convex sets and some more results related to the convex sets. Thank you.